Today, I'm going to talk about ocean-atmosphere interactions associated with Indian monsoon and its variability. In the last talk, we talked about the ocean-atmosphere interaction in the Pacific, and that produces what is known as El Nino and sudden oscillations. One question that was nagging for a long time for the monsoon scientists is that whether similar air-sea interaction is happening over the Indian Ocean and the monsoon region. And for a long time, we thought that the Indian Ocean is just a slave to the El Nino and sudden oscillation, and there is no really independent ocean atmosphere interaction which leads to climate variability in the Indian monsoon region. But that changed with the discovery of the Indian Ocean dipole mode, and I think that made a very important contribution, sort of important landmark in terms of looking at air-sea interactions in the region. So today I'm going to talk about that, but before that, what I'm going to do is talk about what air-sea interactions that take place in this region, not only on interannual time scale, but all time scales, starting from the annual cycle, as well as going into within the annual cycle, like subseasonal oscillations, like the intraseasonal oscillations, and so on. So, so let me start. So we start with the basic, recapping the basic features of the Indian monsoon circulation that we have done over and over again and many times. So I'll not spend a lot of time, but just to remind you that it has this low-level cyclonic vorticity, which is capped by an anticyclonic vorticity at the upper level with a deep baroclinic structure, and it is convectively coupled where the low-level winds are going around the precipitation center, consistent with the response of the winds of heating associated the rainfall. And of course, the rainfall. The rainfall is of course associated with this convergence zone, global convergence zone, and the global ITCZ is definitely associated with the global SST distribution, and therefore there is a potential for the Indian monsoon to be associated with ocean atmosphere interaction. So is there is the Indian monsoon basically intrinsically a coupled phenomenon? We have talked about that Indian monsoon is an intrinsically convectively coupled, that is coupled to the rainfall. The winds are coupled to the rainfall, but is it also coupled to the ocean intrinsically? Without the ocean, will the monsoon not exist, or will it be the intensity and distribution will be quite different? We think so, and why do we think so? That is because if you look at the sea surface temperature or the ocean to the south, and in the Indian continent is surrounded on three sides by the warm ocean, and this I have emphasized right from the beginning. And this warm ocean provides an ample source of moisture, and that moisture is an abundant source of moisture. Essentially, is a source for monsoon, and if that source is controlled by the SST, the variations of the SST is going to influence that variation of the monsoon. Therefore, there is a potential for the sea surface temperatures in this region to be coupled with the monsoon variability. And now, Therefore, let us remember some of the basic features of these, because this coupling between the sea surface temperature and the Indian monsoon will depend on these mean conditions of the SST as well as the monsoon, and that and the mean conditions here are slightly different from that is in the Pacific that I mentioned in the previous talk. So mean features here are the SST is one, definitely most of the year the whole basin is warm, but during the monsoon, due to the winds, the western side is cooler and the eastern side still remains very warm. So there is on the annual mean sense also, therefore, it turns out that and there is a warm pool to the east and there is a colder region to the west, and as a result, our thermocline is also is slanting from west to east rather than east to west in the Pacific. So this is a measure, but most of the time the temperature of this mean temperature is above 27 degrees, and that is critical for producing evaporation because at that point any small changes in the temperature produces large changes in the evaporation, and that is the potential for influencing the convection and monsoon. And obviously this sea surface temperature and the precipitation, which is the ITCZ, is strongly coupled in some sense, sort of qualitatively speaking. If you see the distribution of temperatures and the ITCZ, they are very closely linked. As I said, that the ITCZ tends to be around the maximum of SST in over the ocean, and that ITCZ is associated with the large vertical motion in the middle atmosphere. And so that is throughout the season, this association is very clear. So therefore, there is potential for this the ocean and atmosphere interacting to produce and influence monsoon. More importantly, there is, if you look at what is the net heat flux in the summer and winter, it turns out that this is globally, but over the monsoon region, if you focus in the net heat flux during winter, the northern Indian Ocean is cooler, and whereas the southern Indian Ocean is much warmer. Sorry, there is positive net heat, negative net heat flux. That means ocean is losing heat. On the other hand, ocean is gaining heat to the south. On the other hand, in the summer, it is opposite. The northern Indian Ocean is gaining heat, and that heat is almost about 100 watts per meter square. And so on the average, if you were June, July, August, September also, there will be about 80 to 100 watts per meter square positive and heat going into the ocean to the northern Indian Ocean, and about similar amount of going out of the ocean to the atmosphere in the southern Indian Ocean. So this difference has the potential of changing the temperatures, because if you allow them to hit the mixed layer here, in summer it will continue to heat up, and the temperature, if there is no source, no transport of heat, the temperature in the Bay of Bengal should have increased to about 36, 37 degrees Celsius. However, it is still capped around 31 degrees, 30 degrees Celsius, and that means that heat has to be transported from the north to the south during summer and south to the north in the winter. So that it implies that and that, how does that happen? That is associated, it seems to happen with the help of the atmosphere. So how does that transport takes place? Now, the winds, the monsoon itself determines this cross equatorial wind during summer to be southwesterly in the south and not southwesterly in the north and southeasterly in the south, and the reverse in the winter. But as a result, these winds can have what is known as Ekman flow, and that Ekman flow can produce southward transport in the summer, whereas a northward transport in the atmosphere. In other words, the SST in the Indian Ocean is definitely crucial for producing the maintaining the ITCZ and providing the moisture. But that SST, maintenance of the SST is facilitated by the monsoon winds. So monsoon is produced, the rainfall is produced as a result of the SST, and the SST produces rainfall, rainfall produces winds. Those winds then help transport of and produces ocean currents that transport the extra heat from the north to the south to maintain the temperature distributions as observed, so that to maintain the monsoon at the current level. So, so that is, therefore, definitely there is a ocean atmosphere interaction in this and the annual cycles in the annual cycle itself. So the mean annual cycle of the monsoon is associated with an ocean atmosphere interaction, just like the Pacific, where the Biobioclear hypothesis says that easterlies keep producing the mean SST distribution. Mean SST distribution then warm to the west and the cool to the east produces the Waka circulation. The Waka circulation then intensifies and keeps the SST. Here also, in a way, something similar is happening, and the ocean and the sea surface temperatures help the monsoon rain. The monsoon rain then produces ocean circulation or forces ocean circulation to transport the extra heat and maintain the SST distribution. So there is a ocean atmosphere interaction in the annual cycle as well in this. And this essentially implies that in the ocean, there has to be a shallow meridional circulation. In the annual mean sense, the annual, it should transport additional warm additional heat from north to south, sink here, and then sense of and come back, and then go around that. So therefore, there is a possibility of I mean, unfortunately, there is not enough observations in this Indian Ocean to actually measure this even today. But there are enough indirect, and the models confirm that this must be there. And without that, we cannot maintain this observed sea surface temperature in this. So this is an important part of the monsoon system itself. And this we have seen with the new reanalysis, simple ocean data assimilation analysis. From there, it shows that in summer, it should be transported to the south. And this is a stream function that is plotted here in the ocean stream function. Here, cross sections across the latitude averaged over this band in the longitude in the Indian Ocean. And in the winter, this is opposite. And the annual sense, like what I schematically showed, there is a circulation which should produce transport to the south. And in fact, a strong monsoon, weak monsoon can also change this stream function, so that it also changes the transport similarly. So as a result of this, in fact, this can itself give rise to variability in a way. So the same thing I am putting in this figure again, that the monsoon produces the winds produces transports of heat and maintains the SST, and the SST then actually helps produce maintain the ITCZ and the monsoon. And so therefore, there is this ocean atmosphere interaction on the annual sense. And because of this, in fact, it can even produce, there is a potential that this can produce some year-to-year variations. So suppose you have a strong monsoon and the winds are much stronger, then your Ekman transport will be stronger to the south, and therefore then it will transport much more heat than the average to the south, and therefore leave the North Indian Ocean somewhat depleted in the heat. And because of the heat capacity, the next year it will take much longer time for the radiation balance to warm it, and as a result, it might remain at a cooler temperature to the north, and that cooler temperature to the north will produce weaker monsoon, and weaker monsoon will then produce weaker winds then will produce weaker transport, and therefore leave a warmer North Indian Ocean behind. So this way, it is possible that even this mean meridional circulation, the shallow circulation in the ocean can influence year-to-year variability and interact with the monsoon and produce year-to-year variability. Again, these are seen very much in many models, but observationally, there is not enough support from observational data, and I think this is one area that we need to do some work in terms of collecting good data about the mean meridian, shallow meridional circulation in the ocean. So, with that part on the mean annual cycle of monsoon itself, now let us talk about interannual variability. As I said, for a long time, there was not, we did not know that there is any independent ocean atmosphere interaction within the Indian Ocean basin that could produce a year-to-year variability related to the monsoon. And in 1999, we discovered something called this Indian Ocean dipole mode, and understood that particular oscillation or particular variability involves active ocean atmosphere interaction, just like in the Pacific. And so for the first time, we sort of understood that there is ocean atmosphere interaction very similar to in the Pacific, and would give rise to year-to-year variability of the monsoon or variability of climate in this region. Not necessarily monsoon directly, but climate in the tropical Indian Ocean and the rim countries. So, so what is this Indian Ocean dipole mode? And this was discovered some in 1999. This is some interesting history. This particular work we did when 1997. There was a very big event in this. I'll come back to that in a minute. A very big event in the Indian Ocean where there was cooling in the east and warming in the west. And this event was associated with simultaneously a big event of El Nino in the Pacific. And therefore, there's a lot of interest in studying that. And people started looking at it very carefully. And, and we also looked at it. But when we looked at that particular event, we also realized and went back and in past data and found that similar events were there in the past, and therefore this was this an intense event, but not necessarily unusual. I mean, not necessarily some unique. As a result, so we called it a mode. Simultaneously, Webster and company, Peter Webster is a very well-known Indian monsoon scientist, and they also looked at in 1997 in great details, and they came out with also very clearly and demonstrated that this particular event had a very clearly associated with ocean atmosphere interaction. And so, for interestingly, both these papers were submitted simultaneously, almost same time, and finally, both the papers were published in the same issue of Nature. That was kind of interesting. Anyway, let me. The background to the background of this study is, if you see that associated with El Nino in the Pacific there is some variability in the Indian Ocean. That is what is known as a basin-wide mode. That means the SST over the Indian Ocean changes over the whole basin, and that variability is variability is associated with El Nino, and this has been known, and it was known that this is basically a passive response due to the changes in the winds and the cloudiness and the heat flux affects the SST. So we thought that this variability is rather strong, and people did not know that beyond this there is any other variability in this region and that is the discovery of the IOD was to demonstrate that there is beyond that also there is a variability, and that is associated with ocean atmosphere interaction. One important difference between the Indian Pacific and the Indian Ocean in terms of the year-to-year variability is that the amplitude of year-to-year variability of sea surface temperature here. This is the standard deviation of sea surface temperature of June to September sea surface temperature. And this the amplitude is of the order of 0.4 to 0.5 at the most, on the average about 0.45 degrees Celsius, whereas on seasonal mean like that in the Pacific, it is more than 1 degree. So the Pacific signal on year-to-year variability is much stronger. And this has to do with our basin size, which I'll talk about a little later. So let us keep this in mind. So so what happened in 1997, it was found that during November of 1997, actually the Eastern Indian Ocean was cooler than the Western Indian Ocean. Normally, normally there is the Western Indian Ocean is cooler than the Eastern Indian Ocean. The Eastern Indian Ocean is warm pool. But this particular year, that means there was a considerable amount anomalous cooling. That anomalous, if you take the anomaly, it turns out that there was a huge anomaly about 2 degrees, 1.5 to 2 degrees negative anomaly in this region, and the positive anomaly of about a degree or less in the Western Pacific. So, and associated with this, there was a huge easterly anomaly in the central Pacific, Central Indian Ocean. So this location of the Indian is a very telltale sign where this SST could have affected these winds, or the winds could have fed back to the SST anomaly. Because if there is cooling, the cooling represents a weakening of the heat source there, sort of a negative heat source. Negative heat source means it will be divergence to the west, or the westerly anomaly to the west. Easterly, not westerly, easterly anomaly to the west, and westerly to the east. And so easterly to the east. So there is a divergence from this, therefore westerly to the west and easterly to the east. So this westerly anomaly is consistent with this, and if there is a heating to the increase in the SST, heating is more heating in the atmosphere to the west, then it will be convergence again easterly to the east. That means these Central Indian Ocean, the easterlies will be strengthened by a east-west dipole of this type, and therefore it possibly is associated with the SST variations, and therefore there is a possibility of air-sea interaction, and that is how it was. It started. The story started, and so we looked at in great details, and everybody looked at in great details of how the evolution of this, and so this was a really very remarkable wind anomalies, because normally annual mean sense, the winds in the equatorial Indian Ocean, annual mean wind is almost 0 or 1 meter per second, plus minus 1 meter per second. Now here on the top of that, there are 5 to 6 meters easterly anomaly, which is huge, and these SST anomalies were also very huge. So, but then was it unique? Then when you looked at over a whole period of about 50 years, we found that that is not quite unique, and that we defined a dipole mode index as a difference between the two, the SST anomaly in the east and the west, and the atmospheric zonal wind, the equatorial central equatorial Indian Ocean zonal wind as an atmospheric component of it, because here I can define again going back here, so I can define an equator wind index here, and I can define difference between these two boxes as this minus this as the dipole mode in SST differences as the dipole mode index. And with that, if I plot that, it looks like a figure which is very similar to what you have seen for the Southern Oscillation Index and the NINO 3 in the Pacific. So the correlation is also quite high, and that indicated that. However, there are of course some differences, and the differences are that the events seem to take place much quicker than El Ninos. El Ninos are about separated by 3 to 7 years, maybe average period is about 4 years. But here it turns out that they alternate much more frequently, which seems that their periodicity is lower. And it turns out that the periodicity is indeed about 2 years. So if I do a composite of these, identify some of the major events and look at SST evolution from the peak of the events, going backward and forward by about 1.5 years, and do composite of anomalies of winds as well as the SST. It turns out that of course winds and SST are opposite, but then they change sign in about a year, and that essentially indicates that it has a periodicity of roughly about 2 years. So now how do we say that this indicates that it is coupled? So like in the association between NINO 3 and Southern Oscillation indicated that there is coupling. Here also the association, strong association between the dipole mode index and the equatorial wind index also indicates coupling. But to demonstrate that more clearly, we did some sort of an evolution of these events, and their wind and SST evolution, and their just like I showed in the Pacific that the westerly burst produces Kelvin waves in the ocean. The Kelvin waves in the ocean warms to the east, and the east warming to the east produces again the westerly burst to the westerly anomalies to the west, and that further amplifies the SST to the east, and so on. Something similar we wanted to see, and did a composite of evolution of these anomalies of SST starting at different calendar years: May, June, July, August, September, October, and November, December months. And if you see that in around May, June, it starts with a cold anomaly in the east and a warm anomaly to the west, and easterly winds, weak easterly winds to the west of this cold anomaly. By about June, July, these easterlies start becoming stronger. These are essentially start as a southeasterlies, and then the warming to the north, warming to the west also increases, and as a result of this combined effect, then the equatorial westerly start forming strongly, and by September, October, equatorial westerly anomalies become very strong, and the easterly, the wind anomaly to the negative anomaly to the east and the warming to the west also intensifies. So this indicates that this the cooling produces westerlies to the west, and the warming also produces easterlies to the west, and warming also produces easterlies to the east. As a result, the easterlies are strengthened. When easterlies strengthen, the cooling itself increases because the easterlies will produce the upwelling of the thermocline and downwelling of the thermocline by the Rossby waves generated by these winds to the west. And so there is a clear indication that this evolution is very much associated with an ocean atmosphere interaction. And that is consistent with the increase in precipitation to the east and decrease in the increase in precipitation to the west and decrease in precipitation to the east. And that is something like that. So therefore, the same kind of Bjerknes feedback is operative even in Indian Ocean associated with this mode, where the cold anomaly is triggered by some perturbation can produce easterlies to the west. Easterlies to the west can actually solve the thermocline on this thing and make this colder, and depress the thermocline to the west and make them warmer. And this is just like what happens in the Pacific when there is a warm anomaly, and the Kelvin waves tend to depress the thermocline and make the warm anomaly warmer and warmer, and very similar to that is what happens here in the eastern in the Pacific. So this can be seen in the subsurface temperature as well, and that so if I take a composite of temperature across the equator, 7 degrees south to 7 degrees north average, and then difference between a positive IOD events and a negative IOD events, what you find is a negative anomaly in the east and positive anomaly to the west, which means that thermocline has sold on this eastern side and thermocline has deepened in the western side, as we had proposed as a result of the Bjerknes feedback. So this is consistent with the Bjerknes feedback is operative in this same manner. So what I will do is I'll stop at this point. We'll take a few questions and then come back and talk about a little more different. Try to understand how it is different, how the monsoon actually interacts with this, and how monsoon makes the Earth's interaction different in this, and why this is not a dominant mode in the monsoon region or the tropical Indian Ocean. Okay, so I want to explain. I want to sort of dwell on a few some differences between the Indian Ocean and Pacific, and why this Earth's interaction is interesting and important. And if you remember, the mean conditions in the Pacific is that it is cool to the east and the warm to the west. So the warm pole is to the west. In Indian Ocean, it is cooler to the east, west, and the warmer to the. So the Indian Ocean, Eastern Indian Ocean, is the part of the same warm pool that takes place in the Western Western Pacific. So therefore, the thermocline is also sloping. It is shallow in the east and deep in the west in the Pacific. It is shallower in the west and deeper in the east in the Indian Ocean. So these have some effect on these Earth's interactions. But most interesting thing, of course, is the difference between the Pacific and Indian Ocean is this off equatorial heat source that takes place during summer in the Indian Ocean or Indian Ocean monsoon region, but not in the Pacific. There is nothing like that in the Pacific. Why it is important? These heat source can influence cross-equatorial flow and influence the equatorial easterlies or westerlies. Suppose the monsoon is sometimes strong, sometimes weak, that will change the equatorial easterlies and westerlies. And the equatorial westerlies and easterlies can influence the dynamics of the equatorial Indian Ocean very strongly. So therefore, there is an interaction between monsoon itself and the equatorial winds, which equatorial winds can then influence the Bjerknes effect, and so therefore it is more complicated in this region, and that is It is also more complicated because the mean winds in this region is dominated by a semi-annual cycle, whereas in the mean winds in the Pacific is dominated by an annual cycle. And for the annual mean is in the Pacific is always easterly, and in the central Pacific it is very strong easterly. In the Western Pacific and Eastern Pacific, it becomes a little bit weaker, but it's always easterly. And in the Indian Ocean, the annual mean is actually in the central Pacific, central Indian Ocean is very small, close to zero. And in the West and the East also, their annual mean is only about 1 meter per second. But on the top of that, there is semi-annual oscillation of about 3 meter per second sometimes. Okay, and the 2 meter per second, 2 meter per second. And that can influence when there is a mean is nearly zero, this 2 meter westerly can make the mean wind in the Indian Ocean completely westerly during the May over a large patch of Indian Ocean and maintain it for about a month. And this again happens in October or November, again about 2 meter westerly in the Central Indian Ocean will become, the mean itself becomes westerly. And if mean becomes westerly, it produces something called the Ricci jet, an accelerating jet. It is not just a Kelvin wave which will propagate as a downwelling perturbation, but Kelvin wave will go on intensifying and become a very big depression to the east. And that is what is known as the Ricci jet. So the Ricci jet is also a very, very important part of the Indian Ocean dynamics, and that has to be built into this. It has also an important consequences in these air-sea interactions, and that is why it makes it a little bit difficult to delineate these ocean-atmosphere interaction and what is affecting what. And because of this also, because of the semi-annual cycle, the winds change rapidly, sort of much more rapidly. And as a result of that, the annual cycle itself, the mean wind itself changed so much that the ocean atmosphere interaction cannot be sustained at some point of time. So because of that, also the amplitude of the unstable mode cannot grow to a very large amplitude. So these are some of the issues with the Indian Ocean, and that Ricci jet can be seen in actually ocean observation. It produces very large accelerating jets with open ocean currents of more than 1 meter per second, which is pretty large, and that kind of thing is seen. So we need to keep that in mind in understanding these ocean atmosphere interactions in the Indian Ocean, which is a little more complex than in the Pacific. So this the positive feedback can be understood in a very simple way. Suppose you have started some mean southwesterly, as I mentioned. Suppose the onset, strong onset monsoon can produce a strong some sort of mean southeasterly in this region. The southeasterly can produce upwelling and produce a cold anomaly. The cold anomaly will produce anticyclonic circulation to the west, and anticyclonic circulation will produce equatorial easterlies in this region. Now, that equatorial easterlies will produce then Rossby waves, downwelling Rossby waves on north and south, and this downwelling Rossby waves will depress the thermocline to the west and warm the temperature to the west. Once the temperature is produced warm to the west, it produces more heating to the west. More heating to the west will further reinforce the equatorial easterlies. The equatorial easterlies will further produce colder anomaly, partly by soling the thermocline and partly by producing this upwelling in this region. So there is a possibility of such air-sea interaction in this region. So this is again discussed in this in words in this block diagram. So how can this? So it turns out that IOD is very important and it has its own, sort of ocean-atmosphere interaction. But how is it a dominant mode? It turns out that it is not the dominant mode of variability in the Indian Ocean. If I take the sea surface temperature in the Indian Ocean and do an EOF of this, it turns out that the dominant mode is associated with that, and so basin-wide variability. The basin-wide variability is associated with ENSO. This is in the Pacific, UF in the Pacific. Pacific has this is the dominant, and so is the dominant mode. And there's the Eastern Pacific, and so is the dominant mode. Second UF is like a Central Pacific El Nino. But the second UF is something like what is our IOD? The cooling to the east and warming to the west. And so, and it explains about 13% variance. So the IOD is in a mode, it is important, but it is not the dominant mode. So this is also something that we need to remember. So how could IOD actually affect the monsoon? People have studied and did some correlations and find that there is a correlation between monsoon variability, monsoon variations with the strength of the IOD. During the monsoon season, and it turns out that this correlation, the running correlation, indicates that when the correlation between monsoon and El Nino is strong, the correlation between monsoon and IOD is weak, and currently they are of the similar sort of somewhat similar amplitude. Therefore, they may be important. How can this? How can Indian Ocean dipole actually affect the monsoon? There is a possibility. For example, it produces cooling in the east. You remember this is a wormhole. In this wormhole is where the monsoon ITCZ, the ascending motion of the ITCZ is here in this region, in the oceanic ITCZ. So there is an ascending motion normally. Now the cooling is weakens that ascending motion. So therefore the equatorial ITCZ becomes weaker, and that cooling is favorable for ascending motion in the continental ITCZ, that is over the Indian landmass. So therefore that helps monsoon, is the potential to help the monsoon to become more vigorous. And the Western Indian Ocean being warm produces, this is the region through which the cross-equatorial flow brings moisture to the Indian landmass. And here it is being warm, there is more moisture available, more moisture convergence to the Indian landmass also can influence and invigorate monsoon. So there is a potential is there that this IOD can facilitate strengthening the monsoon. But the correlation appears to be not very strong, but that possibility is there. When we did a sort of nonlinear causal inference calculation with these and the Indian monsoon, it turns out that the correlation, I mean, the association is rather sensitive to what data we use, and therefore I still feel that this association with IOD and monsoon still needs more investigation. So with that, I'll stop this and then talk about stop this discussion on the ERC interaction on internal time scale. So of course, this cooperation between the atmosphere and the ocean makes the extreme large climate very unique, and makes it very also interesting because it produces a lot of interesting variability. So let me talk about now another time scale where ocean atmosphere interaction can also influence the variability. It is in the intraseasonal time scale. I mentioned about these monsoon intraseasonal oscillations, and we find that even in this time scale, there is a certain amount of ocean atmosphere interaction is taking place and affecting these oscillations. it is it is possible that these oscillations do not need the ocean even if the SST is fixed, you can possibly get through atmospheric processes, we can get oscillations in the atmosphere of this time scale, but their structure and periodicity could be different completely. And what we observe, the observed structure, spatial structure, propagation characteristics, as well as the periodicity, is a result of this interaction with the ocean. So ocean atmosphere interaction, how do you actually see that there is ocean atmosphere interaction on this time scale? So you take out that time scale, 10 to, let us say, 80 day, that is where your biweekly as well as the 30 to 60 day mode are there. So you put them together and filter the data and look at the variations or the northward propagation of this OLR, outgoing long wave radiation, which is a representation of sort of association of rainfall. You can actually look at actual rainfall, but OLR is equivalent and then you look at variations of SST across Bay of Bengal region, 85 to 90 degrees east, and around which as a function of latitude. If you look at, it turns out that it has the clear northward propagation, which we have already discussed. It turns out that SST also has that same kind of northward propagation, and so it SST. North Bay of Bengal has large variation of SST, and that variation of SST are strongly linked with the surface wind speed variations, which also have an outward propagation, and net heat flux going into the ocean, and that also has an outward propagation and has the same periodicity, and of course are related to each other. So how this can affect is the SST can produce cloudiness and winds. Clouds will produce winds. The winds and fluxes of evaporation, the latent heat fluxes, and it will affect all these will affect the QNet. Then QNet drives the SST. So therefore, the atmospheric processes through cloudiness and the winds affect the QNet. SST affects those clouds and the fluxes, and the fluxes give rise to QNet, and the QNet can then affect the SST, and that seems to what happens. And this has been. It turns out that there is a phase difference between the SST and QNet, which is just about a quarter period difference. So they are in quadrature, which indicates that the SST variations are driven by the QNet. So that we can establish. Having established that, then we see that the QNet is affected by the atmospheric processes, wind speed, and all the other things like the OLR, and therefore the atmospheric processes are affecting the QNet, and QNet is affecting the SST. SST is affecting the atmospheric processes. So there is a feedback between them, and that is this. Therefore, this, if you do a sort of composite, lead-like composite of rainfall and the SST, by taking a reference time series over the Bay of Bengal around 15 degrees north, and then if you do a lead-like composite of rainfall itself with respect to that time series, then obviously we see a northward propagation of the rainfall, and then do the same thing for the SST. And what we find is that the SST becomes maximum and positive anomaly not during the monsoon, not during when the rainfall is maximum, but before that, and when rainfall becomes maximum, SST starts cooling and becomes significantly negative after the rainfall. So this essentially means that the SST helps producing the rainfall. It is required to produce, but once the rainfall takes rainfall produces clouds, clouds produces cooling, and at the surface the cooling, then clouds as well as the fluxes produce cooling, and cuts down the solar energy and cooling, and therefore SST weakens. When SST weakens, the precipitation itself cannot be maintained beyond a point, and then the precipitation is weakened. And when precipitation is cleared up, then when there is negative, there is no precipitation, negative precipitation, that is when SST warms up. SST becomes hot, warmer when there is no cloud, and then the surface becomes warms up, the SST warms up, and when the SST warms up beyond a point, then the convection can start again, and that is how they seem to be related to one another. And this can be seen from the relationship between the SST composite and the different fluxes. Most of this is the SST becomes peak before the rainfall, and then once the rainfall becomes, SST start declining, and that declining SST is due to due to short wave flux being cut down, and the latent heat flux also being adding to that, and so there is a feedback between these processes, which can lead to the interaction between SST driving the rainfall, but the rainfall is affecting the SST, and then coming back again due to radiative processes. The same thing actually happens even on a 10 to 20 day time scale, and then same thing, same lead-like composites can be done, and this 10 to 20 day is a westward propagating rather than northward propagating phenomenon. And if you do the similar composite, you can see that SST is positive in the negative phases of this, and then that tries to drive the precipitation, and then when the precipitation becomes strong, positive, SST cools down and kills itself, and then again when it clears up, the SST becomes positive. So that again seems to have a similar association. And in fact, this this ARC interaction in the 10 to 20 time scale has now come out, and even on salinity and other things in the North Bay of Bengal, this 10 to 20 day fluctuation in the ocean are very clear and very dominant. And I had mentioned in the last in the other subseasonal oscillations talk that in the equatorial region there is in this region there is a large biobioclear oscillation, but it is now known that in the ocean, both salinity and temperature, there is a strong biobioclear oscillation in the Bay of Bengal. And this is during our monsoon mission. There was a special mood buoy. There was a couple of mood buoys already there from the MOES Rama buoys, but in addition to that, there was an Seoul Oceanographic Institution had put up a special mood buoy where the fluxes and other things were a lot of other measurements were there. And during the the data over there, several years of data over there, this is 1916 and 1910 to 17 data are available in this region, and this data shows that within each season there is a lot of this biobioclear oscillation, and the biobioclear oscillation, there is an annual cycle, but apart from this annual cycle, there are considerable biobioclear oscillation in both salinity and temperature. And they found, this is a study by ISC group, Sri Lekha Sengupta, and also people involved from the Woodsole. They showed some very interesting interaction, sort of possible ocean atmosphere interaction in these time scale. So over this mood buoy, the SST and QNet again has a quadrature relationship. So if you plot the dt and the time derivative of the SST and QNet, they seem to really match each other, which indicates that QNet is actually driving these. And the QNet is, of course, affected by the fluxes which are driven by the atmospheric processes, the variations of the OLR and cloudiness and winds on that Biobioclear time scale. And the salinity is affected by, is also very interesting, salinity fluctuations in these, which are found that these salinity fluctuations are actually driven by the atmospheric bionuclear oscillation driving ocean currents. So atmospheric bionuclear oscillations, you remember, it had these double vortex structure, Rossby wave structure. These Rossby wave structures seem to drive these fluctuations, and in the not in Bay of Bengal, there is a low salinity due to the Ganges Brahmaputra discharge, Brahmaputra Irabati discharge. There is a very low salinity region, and this low salinity is driven by ocean currents, which are driven essentially forced by the atmospheric vortices, and that ocean current brings low salinity from time to time, and that is seen in this mood buoy position, and that fluctuates with these 10 to 20 day time scales, and because these currents also fluctuate with this time scale, and those currents are caused by the atmospheric winds, in that time scale, which are essentially those Rossby waves. So it indicates again a process of ocean atmosphere interaction that can produce salinity variations and temperature variations in the North Bay of Bengal, which is largely driven by the atmospheric bionuclear oscillation. So it does not indicate the feedback, which is something that I think we need to further understand. Okay, with that, I think I will come to the almost end to this. So one other example I want to give, even on this. So I am coming from the interannual time scale to the seasonal cycle, and then I talked about subseasonal, intraseasonal oscillations on 30 to 60 day time scale, even on the 10 to 20 day time scale. Ocean and atmosphere are interacting with each other all the time, and each time scale is affected by ocean atmosphere. Even on synoptic time scale, like the tropical cyclone, can influence the ocean and influence the tropical cyclone itself sometimes. And for example, this is again a study by Sengupta and company, and they have done some composition of several of these tropical cyclones in the pre-monsoon Arabian Sea and Bay of Bengal, and in the post-monsoon season, and only in the North Bay of Bengal. So in the Arabian Sea and the pre-monsoon season, even over Bay of Bengal, the cyclones seem to these are different cyclones at different directions, different positions. What they have done is sort of brought them back into sort of same timing, and then from that timing along the track, how it cools the ocean. And it turns out that a cyclone, when it passes through, it will cool the surface temperature due to two things. One is, of course, it will strong which will produce evaporation, evaporative cooling will be there. But in addition to this, in more than that, the strong which also will produce mixing from the subsurface water. The subsurface mixing through turbulence can also cool. And it turns out that sometimes it cools quite a bit, up to about 3-4 degrees, especially in the Arabian Sea. But in the post-monsoon, during Bay of Bengal, this cooling is rather weak. That is because now after the monsoon, there is a lot of fresh water, and in the North Bay of Bengal has a large stratification. So the upper layer is light, and therefore the mixing is somewhat inhibited. As a result, the cooling also becomes weak. But on the other hand, in the pre-monsoon, there is not such cases, and therefore, and especially in Arabian Sea, there is no such fresh water, and therefore the mixing, the strong mixing can actually cool very rapidly. So, and suppose this happens, and if by the large scale circulation the cyclone stands over there, it automatically will kill itself, because that is what happens sometimes. Because if it becomes stationary, it will kill itself. Because cyclone keeps moving, that is why they survive, because they basically cool the surface as they slowly move. And so that is one sort of an air-sea interaction that is possible with the tropical cyclones. And with that, this is just giving an example how they can interact and how they can affect each other. So I think in conclusion, Indian monsoon region with the continent surrounded by warm ocean on the three sides is a region where vigorous convective activity can flourish, making Indian monsoon a convectively coupled system, which we know. But for the same reason, it is also a region where vigorous ocean atmosphere interactions can flourish, shaping monsoon variability at all time scales. So therefore, it is a region where we have a lot of activity going on, and that makes it also a little more difficult to predict it, because they can give rise to a certain amount of chaos. So with that, I will stop here.